The first speaker is Takashi Tanayanagi. Excuse my Japanese. Okay. Who will speak on formal theory developments.
Okay. First, I'd like to thank organizers for inviting me to this really wonderful conference. So I'm working on string theory. I'm a little bit outsider of this compared with the topics of this conference. So following the organizers' advice, I'd like to start from some story related to black holes and Bekenstein-Hawking, black hole entropy, and going up to the recent development of string theory. So this title is from black holes to qubit. Qubit means some quantum information. And this leads to the idea of the space-time emerges from quantum information or quantum entanglement. That's what I'd like to talk about today. So let me begin with the introduction. So as we know, so in biology and chemistry and condensed matter physics, so various kinds of microscopes plays a very important and crucial experimental device. And as in this main topics of this conference, so particle physics and nuclear physics, accelerator plays a key role, and it's analogous to the sort of microscopes to probe the deep microscopic physics. But then my question is that what are the useful microscopes in string theory? And string theory is supposed to be a promising candidate of quantum gravity, so this is a kind of microscope for gravity. What is that? But before I go into that, I'd like to briefly explain what is a string theory. So string theory, the idea is that we just replace particles with strings. So elementary constituent of material is actually not the particles, but the strings, to understand some quantum gravity. This is the idea of string theory. And as you see, there are two kinds of strings. So one is an open string, which two endpoints. And endpoints, we can associate some charges. So this describes charged particles and gauge interaction, so quark and leptons, and their interactions. And there are another kind of strings called closed string. So closed string, actually no endpoints, so there are no charge. But actually, this describes at the low energy spin 2 particles like gravitons. If we have a supersymmetry, we can describe supergravity by looking. So string theory combines these two different, very important ingredients of the our universe, so particles. But however, so please don't ask me a question like, maybe this is something you are mostly interested in, but how to derive standard model from string theory, why we live in 4 dimensions, and how to realize De Sitter space, which is important for inflation, in some very controllable way in string theory. So these are, of course, very interesting questions, and there are many interesting developments, but I think it is still too far from the complete answer. And instead, I'd like to focus on another aspect, which is more theoretical aspect, which is deeply connected to gravity. And what's the quantum gravity, which is described by string theory. And so the recent studies for these 10 years or 20 years clearly suggest that the microscope in strings, useful microscopes in string theory actually is provided by so-called idea called holography. Or expressed example is so-called ADS-CFT correspondence and gauge gravity correspondence. And holography is not a real experiment, but provides very useful thought experiments. Historically, the most important hint of holography, So hints of the holography origins from the famous Bekenstein-Hawking formula, which discovered more than 40 years ago of black hole. So this formula is still very mysterious even today. Maybe I might think this is much like something we call all parts. So that means that includes too advanced knowledge to digest for a short period, even after 40 years, more than 40 years from this discovery, still we don't understand the basic interpretation of that. So the reason is that, so basic question is like why we have entropy in a classical theory. So general relativity is a classical theory, and we know entropy arises when we quantize the system in statistical mechanics. But however, entropies exist even in classical theory, and the related question is what is the structure of Hilbert space in quantum gravity. So we still don't know the clear answer to this question. But this formula stimulated a lot of recent active progress of the gravitational aspect of string theory, especially in the end we reach the idea of this emergent spacetime from quantum entanglement. Sometimes we call it just idea of it from qubit. And so we see that some number of papers with abstract, which includes entanglement, keyword quantum entanglement, it's rapidly increasing these days. But there are some major developments I will going to discuss later. So this contents of my talk is like this. So we just finished the introduction, and I'm going to explain the connection between black holes and string theory, and explain some aspects of the holography motivated by these black holes, and then end up with some recent idea of this emergent spacetime from quantum entanglement. So let me begin with black holes. And so nowadays, black holes are getting very familiar astrophysical objects. And there are many discoveries, especially most remarkable one is gravitational waves from the merger of pair of black holes, which we noticed recently. And so it's getting more familiar object. But nevertheless, there are deep questions, and black hole can be produced after gravitational collapse of very heavy star, like this. So star collapses into black holes, and once it collapses, observer outside of the black hole cannot see inside the black hole. So that means original information of the star, like how many particles and so on, so it should be included inside the black hole. So black hole should carry quite a lot of hidden information inside. So this amount, the amount of this hidden information in black hole is measured by a black hole entropy. So now we come to this Bekenstein-Hawking formula of black hole entropy. So this is a very beautiful formula, and which measures the amount of information inside the black hole. It takes a very simple form like this, and discovered by this Bekenstein and Hawking. And it was quite sad news that Hawking just passed away this year, and Bekenstein also passed away a few years ago. But nevertheless, this formula is pretty remarkable and still quite alive even now, and maybe in the future. That so you see this formula is very simple and includes all basic physical constant, like velocity of light and Planck constant and Newton constant and so on. And also it involves geometry because this black hole entropy is proportional to the surface area of black hole. So to understand this formula, we have to combine geometry and gravity and quantum mechanics. So namely, this is a theory of quantum gravity. So without understanding quantum gravity, we cannot understand this formula. And anyway, so the most impressive part of this formula is that its entropy is proportional to the area and not to the volume. Usually, in thermodynamics, we know the entropy is proportional to the volume. It's extensive, but here it's not true. But nevertheless, this formula satisfies first law and second law, such as thermodynamical laws. So this still, at that time, it's quite mysterious, but nowadays we have a nice interpretation owing to holography. So holography, so now I would like to explain holography. This is first noticed by Tofuf and Susskind more than 20 years ago. So idea is just because, so we have entropy proportional to area, that is unusual, but maybe this means that degree of freedom in gravity is one dimension lower than usual materials. So if we think about, so if we go a little bit further, then we can think about some gravity on some manifold M, and this degree of freedom is actually one dimension lower, so we can project degree of freedom down to its boundary. So boundary is here, so one dimension lower. And so this theory should be standard quantum theory, quantum matter theory. So maybe there are such an equivalence. So this is a very, this is quite conjectural, and it's very heuristic. But we have some nowadays nice example, expressed example called area safety correspondence. I will come back to this later. But let me a little bit turn to black holes. So we'd like to understand the origin of black hole entropy. So if string theory is a really nice, well-defined theory of quantum gravity, we should be able to understand it. At least give some microscopic explanation of this black hole entropy. So to make a black hole, so we need So we need a very heavy object. And for heavy object in string theory, it's a quite useful object. It's called D-branes. So we have D-branes. We have D-branes here, and D-branes defined by some hypersurface where open string attached. But you can think this D-branes as a coherent state of strings. So if you have a lot of, chunk of strings, so that you can put a little bit of strings, then looks like the same picture, like this. So this object, D-branes, first considered by Joe Policzynski. So it was another sad news that he passed away this year. But this is a quite useful object in string theory, so we can make up black hole by using this. So here are the sketch. So we have some observer sitting outside of the black hole. This is actually Japanese word of black hole. And the Hawking radiation coming out from that. But the observer cannot see inside. But string theory and holography provides a useful microscope to magnify the region inside the black hole. So if we see this through this microscope, we see D-branes, a lot of D-branes, which I mentioned, very heavy object, and a lot of open strings attached. So black hole, especially the supersymmetric black hole, is interpreted as D-branes and open strings. So we can count number of open strings and explain black hole entropy. Indeed, so this is the final formula, first noted by Strominger and Buffer, and we can count number of open strings and precisely agree with Bekenstein-Hawking entropy. So this is a string theory derivation of black hole entropy. So, but now, so this black hole entropy story can be generalized. So this is actually the philosophy of holography. So we have some gravitational theory, but if we look gravitational theory through some microscope, we see some microscopic degree of freedom, like given by some quantum manifold systems or gauge theory or some quantum field theory. So this is the idea of ADS-CFT correspondence. So we think ADS-CFT correspondence argues that gravity or string theory lives on d plus one dimensional anti-de Sitter space is equivalent to conformal field theory, which lives on the boundary of this anti-de Sitter space, namely d-dimensional Minkowski space-time. So this is anti-de Sitter space is a maximally symmetric space with negative cosmological constant. So negative cosmological constant may be not phenomenologically favored, but anyway, this is a real theory, and negative cosmological constant is quite frequently appears in string theory and plays a very important role here. And this is general relativity. So if we take a classical gravity limit, we get the general relativity. We forget about quantum corrections or quantum gravity effect, and this limit exactly corresponds to the strongly coupled limit of gauge theory. This conformal field theory is a massless quantum field theory, and typically gauge theory, and the SUN gauge group. So this, we take a Lagian limit and strongly coupled limit, they actually considered to be equivalent. So this is the ADS correspondence, and explicitly the physical relation is given by just equivalence of this equality of partition function. So this ADS-CFT is derived roughly this sort experiment. So we can think about this a lot of chunk of D-branes, a lot of D-branes, and they are very heavy, so that following general relativity, it curves. We get a curved space-time, and this is precisely coincide with what we call anti-de Sitter space. So these two theories should be equivalent from the viewpoint of string theory. So there are a lot of open strings and D-branes that makes SUN gauge theory if you have n D-branes. On the other hand, here we have a theory of closed string, namely gravitons. So these two theories are equivalent. This is a claim of ADS-CFT, and this is a metric of anti-de Sitter space. This is a Minkowski space, but with one more dimension. This is a Minkowski space, but we have one more extra dimension here. So this is a z direction. And if we take a particular situation with black hole, so then we can think about thermodynamics of black hole. So as we notice, the black hole entropy and free energy and temperature, Hawking temperature. So that thermodynamics precisely coincide with thermodynamics of this gauge theory. So there is such a precise equivalence between them. So this ADS-CFT actually origins from open-closed duality. That means if you think about cylindrical string world sheet, so if we cut vertically, you get a closed string. If you cut horizontally, then you get an open string. But this string is just made of same material, same roots. So this should be two different ways of looking, but they should be equivalent. We know this is the origin of ADS-CFT. However, there are no complete proof of ADS-CFT so far. So this is a quite important future question. And however, nevertheless, we have quite a lot of evidences so far, like this order. So many papers written to confirm this duality, so there are no doubt. So string theory don't doubt this correspondence, but proof is still missing. Thank you very much. So, but we have to be a little bit careful that, so here we talk about the gravity, but the classical gravity only appears when we consider strongly coupled gauge theory. So these two theories are equivalent. And the typical example is related, some similar example is a gluon plasma, cold atom system, and high TC superconductors are some analogous to this situation. And as we know nowadays very well, so the famous plot of this viscosity entropy ratio, so this is just water here. But this is a gluon plasma, has a very low viscosity, and the ADS-CFT result given by a beautiful formula, eta over S is the entropy density, is equal to 4 pi, and this is very close, similar value of this viscosity is observed in really experimental way. So, but anyway, we are looking at such a theory. So Einstein gravity is dual to this theory, but this theory is rather weakly coupled theory is related to more quantum gravity theory. So, but there are recent updates. Maybe I should mention this very interesting result about quantum chaos. And chaos is characterized by so-called Lyapunov exponent, where these two classical trajectories separated and the time evolution, how much they separate. And this is a quantum analog of this. This is so lambda, if lambda is larger, then chaos is larger. So an ADS-CFT have a very characterized value, very beautiful formula, given by this formula. So T is the temperature. And Amartya Sen and Schenker and Stanford shows that this has some upper bound. So in any quantum system, Lyapunov exponent is bounded by this value. And indeed, this maximum value is given by this ADS-CFT. That means really strongly coupled and related to previous comment. And we can also derive some specific heat, some constraint for interacting metals by using ADS-CFT. So if we assume existence of Fermi surface, then specific heat behaves at low temperature to some power, but this power turns out to be always less than 2/3. There are some, you can prove this by using ADS-CFT, and this, but we know alpha equal 1 is a standard metal, like lambda Fermi liquid, so this suggests that strongly coupled theory has a totally different physics and something called non-Fermi liquid in condensed matter physics. So that way, so we get some bounds in various cases. And so now I'll switch to the final topic of this talk, but of course related to previous this holography. This comes from actually holographic idea. So namely connection to quantum information, especially quantum entanglement. What is a quantum entanglement? So quantum entanglement is a quantum correlation between two subsystems. Simple example is two qubit systems. So we have two electron spins, A and B. And if we assume some direct product states, there are no correlation between them. So always A spins up and B spins down. There are no entanglement. But entangled situation is like this. So singlet state of spins. If A spins up, always second spins down. And if A spins down, then B spins up. So that case situation, this is called Einstein-Podolsky-Rosen state, EPR state, or Bell state. It's a maximally entangled, this two-qubit system. This is entangled. So we are interested in more this entangled situation. And so entanglement entropy, so this amount of this quantum entanglement measured by so-called quantity called entanglement entropy. And this is roughly speaking that just counting number of EPR pairs, these entangled pairs. So, and more precisely, we can define this way. So we have decomposed Hilbert space into two parts, and define so-called reduced density matrix. We just trace out this extra part, B, and just keep information for A. So we lose some information in this process, and finally, we just compute von Neumann entropy, rho log rho minus rho log rho. This is a definition of entanglement entropy, and measures the correlation between A and B. So this quantity is quite important, especially also in quantum computing theory that measures some amount of resources. And also, as we mentioned, this also plays very important in the context of gravity, and especially holographic principle. So this is so if we think about this computation of this quantity, entanglement entropy, by using ADS-CFT, we have a very nice, very simple result, and which is very analogous to the Bekenstein-Hawking formula. So this is a kind of generalization of Bekenstein-Hawking formula. So if we think about this anti-ADS CFT, so this anti-Doshita space gravity is here, and this is the boundary. And we think about the division A and B, and we talk about entanglement entropy for this region. So this entropy, information included in this region, is measured by the area of this surface which covers over region A. And especially this is given by minimum area surface, which attached on the boundary of A. So this is a kind of generalization of Bekenstein-Hawking formula. Thank you very much. But more universal in that we can apply this into any different setup where this surface is no longer a black hole horizon. But this formula is also proved by Lukowitz and Marder-Senna in 2013 based on this ADS-CFT principle. And so there are recent updates. So we can actually, this surface is the region surrounded by the surface, and A is actually, this region is dual, equivalent to the this information included this region in the gravity is equivalent to the information of the gauge theory at this boundary region A. This is called entanglement wedge. And also we have some generalization of this formula for mixed state, but I'm not going to details. And so we can have a nice connection between this entanglement entropy and Einstein equation. So there are some dynamics of this Einstein equation, dynamics of entanglement is captured by so-called first law, and which means the entanglement increasement is same as some energy increasement, like first law of thermodynamics, but this energy is something called modular energy. But this actually turns out to be equivalent to perturbative part of Einstein equation, so we can understand gravity dynamics by just in terms of entanglement dynamics. And finally, I'd like to mention the emergent space-time from qubits. So this holographic formula, this entanglement entropy, and its holographic computation suggests that there is actually 1 qubit of entanglement for each Planck length area. So we can think about this surface, which we compute entanglement entropy. So it's like this. And this Planck length, for each Planck length on this surface, we have 1 bit of entanglement. So and we can change the position of A and as much as we like, as opposed to black hole entropy. So that way, maybe space-time can be consist of qubit or entanglement. This idea is manifest in the framework called so-called tensor network. Tensor network is a graphical description of quantum wave function, and like this. So especially tensor network called MERA is supposed to be describe conformal field theory, gapless state. And there are conjectures that maybe time slice of anti-Doshita space correspond to just some tensor network, like this MERA tensor network. So it looks like very similar, and this means that collection of entanglement makes up the space-time. If we compute the entanglement entropy, also counting number of these bonds, and this is corresponds to the finding the minimum area surface here. And so this looks like a very static idea, but we can see some dynamics from this tensor network viewpoint. So the entanglement, time evolution of quantum entanglement is, you can plot this like this. So then you could see some sort of propagation of waves, and this looks very analogous to the gravity. So, and as already mentioned, Einstein gravity, Einstein equation motion can be derived from entanglement perturbation, some dynamics. So in that sense, gravity dynamics can be captured by entanglement dynamics in quantum manifold systems. And finally, just want to mention the ER equilibrium conjecture made by Marder-Senna and Susskind. So this idea is just closely related to the previous one. So actually, this idea is naturally realized in ADS tensor network picture. So this means that if we have some quantum entanglement between two regions, A and B, then geometrically we can understand that actually the existence of some wormhole between A and B. So this wormhole is something like Einstein-Rosen bridge, which appears in the eternal Schwarzschild black hole. But also, there are some recent updates by Gao, Jafari, Swo, that if we also introduce, originally they are entangled, A and B are entangled with each other, but if you introduce some interaction between A and B, suddenly this wormhole becomes traversal. Originally, this wormhole here, Einstein-Rosen bridge, is not traversal, even though geometrically connected, but there are no time-like paths which connect these 2 points. But now if we introduce interaction, so this becomes traversal that way. So this, quantum information theoretical procedure is reflected back to the geometry of gravity. So this is a recent interpretation. And this process is very closely related to famous phenomena called quantum teleportation. Okay, so these are all of my talk. So this is my summarized conclusions. So far there are many efforts to understand the Bekenstein-Hawking formula, and they lead to the holography, idea of holography, and which plays a very important role in the string theory these days. And ADCFT provides a very powerful tool to study quantum gravity or even its definition. So because we can define gravity, quantum gravity, by using just a gauge theory. And the study of quantum entanglement in ADCFT inspires the new idea of emergent spacetime from quantum entanglement. And tensor network is one explicit framework to work with, and there are possibilities that this realizes this idea of this emergent spacetime. So this is currently ongoing directions. And we see that area of minimal surface is interpreted entanglement entropy. And there are recent developments, first conjectured by Susskind, and there are more recent updates now. But we can look at also volume. So what about volume? Actually, volume of time slice is interpreted some quantity called complexity. Complexity is a measure which measures the state, is how much state is complicated. So how many steps we need to produce such a state from simple state. So that way, so we have many interesting probes to look at this ADS-CFT correspondence or holography. So here are some future problems. So thank you very much. I think I'll stop here.
We have time for some questions.
When you make the correspondence between the gravity and the anti-de Sitter space and the conformal system on the other side, what is that and your cosmological constant is negative? Is it finite?
Cosmological constant is finite, yes. That's related to the degree of freedom of the dual conformal field theory, namely so-called central charge. It's finite and negative.
Any other questions? No questions? Let's thank Tadashi again for a very nice talk. Our next speaker is Kate Shaw, who will speak about outreach and education.
Okay, thank you very much. Good afternoon, everyone. So I'm going to be presenting the outreach and education on behalf of the 4 LHC experiments, ATLAS, LHCb, ALICE, and CMS. Okay, so I'm going to begin by talking a bit about why we do education and outreach. So we all know as scientists, it's our responsibility to communicate and to educate our audiences. So this is students, teachers, and publics throughout our countries. And we do this to stimulate interest in particle physics and nurture support for particle physics. And by doing this, we contribute to increasing the scientific capacity within our nations and to motivate the next generation of scientists. So the key messages all 4 of the experiments include our physics. So we want to talk about what we're doing and why it's interesting. We want to talk about our detector, the software computing, our technology. And we want to talk about our collaborations and our diversity. Another thing the public are often very interested to talk about is what is the value and the impact of fundamental science in society, and in particular of particle physics. And this is something that often seems very obvious to us as scientists. So we have to effectively communicate what the value is of our science, of our scientific methods, our technologies, and of course our physics and our discoveries and what impact they have on society. So I'm going to talk a little bit about the different ways we communicate from the different experiments. So these involve doing things like public events and exhibitions, talks and having online websites. We have virtual visits, social media, multimedia, and masterclasses. So starting with exhibitions. So all 4 experiments have very nice visitor centres. The ALICE experiment has a very nice visitor centre that you should see if you visit CERN. You can see it includes a full-scale mock-up of the detector. It has information about how they do particle identification and a periscope showing the cavern, and it has a film about ALICE, which shows its history, physics, and information about the detector. The LHC-B detector also has a very nice visitor centre, and they've just made a very nice mural on the floor. So this is exactly above the LHC detector underground and a 1-to-1 scale. You can see they have the LHC elements pointing at a detector, a poster of the detector, and a nice visitor stand. So of course, many of us in the different experiments do public events and public talks, and this is a fantastic way of communicating directly your passion to the community. So these can be talks and events that we host at universities, at schools, at science festivals, and more people are looking to engage new audiences. So maybe giving a talk on a beach or in a pub, at a cafe, or at a music festival. So here at ICHEP, they had a very nice outreach program. There was 2 public talks. One is going to be this evening on quarks and the cosmos. They had a nice science festival on Sunday, and they had a very, if I can make the video, they had a planetarium. This was working with Berkeley and Atlas doing a planetarium called Phantom of the Universe. So this is showing, this is to immerse audiences in the search for dark matter. So this is translated in many different languages, and it's for free. So if you're interested in having this planetarium, you can get in touch. So all the experiments have various resources that they create for these different exhibitions. So CMS, Atlas, LHCb, and ALICE all do things like brochures, they do books, fact sheets, posters, and postcards. ALICE make these very nice paper, make these very nice paper mock-ups of the different detectors. And Atlas also do this nice colouring book that's available for preschool students. And there's also the LHC Lego and different Legos that you can get of the different detectors. These are great ways of being able to communicate our information about our detectors and our physics events. So moving on to education and masterclasses. So masterclass is one of the most fantastic ways we can talk about particle physics with high school students. So this is 16 to 19-year-old students. So the masterclasses are organised by the International Particle Physics Outreach Group, IPOG. You can visit their website where they have a bunch of different resources for outreach in particle physics. So the idea of the masterclasses is that high school students get to be a particle physicist for a day. They get invited to a nearby university or research centre, and they have lectures about particle physics and about the detectors. They may have a tour around the labs, and then they get to analyse real data from one of the 4 experiments. Okay, so they do this using event displays, and they do a real analysis and then compare their result to theory. This might be searching for the Higgs boson or reconstructing the Z boson or the D0. So the nice thing about the masterclasses that happen in spring is at the end of the day, 4 to 5 different universities that did the same experiment get to meet up in a video conference. So it's moderated by some people at CERN, and 4 to 5 different universities from around the world compare results and discuss. So you can see the different experiment masterclasses here, and if your university is not involved, please get in touch. We can help you organise them. Okay, the experiments also organise virtual visits. So this allows people from all over the world to come and have a tour of one of the experiments from their university, or this can be done at a science event. Okay, so you can see here Atlas, Atlas, ALICE, CMS, and LHCb all do virtual visits. So you might be in a school or at a science event, and they get to have a video conference live to scientists in front of their detectors or in their control rooms, where they get to give them a tour around and answer questions. Okay, so of course all the 4 experiments have public web pages, which are all absolutely fantastic. I haven't got time to go into everything that's on them, but of course they talk about the physics, the detector, the collaboration. They've access to lots of different resources. Some of them have these really nice interactive event displays, such as the LHCb collaboration, and they do a host of different communications. So this is updates, news, and Atlas does portraits and physics briefings. And all the experiments, of course, do social media. So social media is extremely important to communicate to a wider audience online. So all 4 experiments, again, have most of the platforms. So this is Twitter, Facebook, Instagram. Some also will do Google+, Flickr. So this is Twitter, for example, for Alice. They have roughly between 30 and 60,000 followers on each of the different experiments. This is pretty good compared to similar size experiments. It's a great way of showing photographs. This is a nice post jointly from Atlas and CMS to celebrate a few days ago the Higgs birthday. And of course, it's a great place for posting multimedia. So maybe during the shutdown, upgrade, or CMS did these nice selection of 6 videos about the Higgs boson. So now I'm going to talk a bit about challenges we have in communication and outreach. One of the big challenges all 4 experiments are discussing at the moment is how to communicate our physics better. Okay, so one of the ways that we're doing this at the moment is creating better ways of drawing and making graphics of the physics. So for the recent TT bar, the TT Higgs production observation, CMS and Atlas both made very nice videos. I'll just give you a little video of the GIF that Atlas made to try and describe the TT bar production. So these are really important, and it's great that all the experiments are making these sort of videos to really be able to describe to non-expert audiences exactly why these results are so important to us. LHCb are currently working on a fantastic video looking at the whole process from event selection all the way to publication. For their very exciting base sub-S to mu discovery, so this should be out soon. Atlas also worked to communicate the physics better by making physics briefings. So you may have noticed several coming out during the week. They come out at the same time as an exciting paper we might have coming out at a conference, and they try to explain why the paper is exciting and what the physics is and what the physics means, again, to a general audience. Okay, the next challenge I'm going to talk about is how we do education for the next generation. So the masterclasses are absolutely fantastic, and I really advise everybody to take part in them. However, they really are just 1 day, maybe 2, of looking at event displays. So the experiments have looked at how to get their data out for people to analyze. So all 4 experiments are involved in the Open Data Portal at CERN, so you can go and check out the portal here. The idea is to give access to the open data, make it usable for education and teaching. So this means providing software, tools, and of course, documentation. So I'm just going to focus a bit about CMS and Atlas's open data. So CMS have a very wide audience for their open data. So they want their open data to be used for physics research, for data science, for research education, for high school education, and of course for outreach. So they have downloads available for their data sets, which include, their data sets are in AOD format. They have also simulated data. You can download a virtual machine to run the software off. They have analysis examples, event displays, which you can see up here, and lots of software. And their open data has also been used for research. There's 2 papers come out on theory using the open data from CMS. So Atlas, along with using the Open Data Portal, also has made an educational platform. So the idea of this website, which you can follow the link there to, is to give people that come to the website step-by-step instructions of how to use the data, tutorials, and they also have access, of course, to data sets, which in this case are in root format, simulated data, software, virtual machines. So there's 3 levels that Atlas have created. The first level is actually just visualization. So without downloading any data, it means that students can play around with these plots. Here's a GIF showing how you can click around on these plots. There's a HWW, WW, TT bar, and Z. So by making different selections, you can zoom in on the different signal regions. Along with visualization, they can also access the root trees themselves. There's root books, which I'm going to talk about on the next slide. And you can download the full data set and the virtual machine. This is also all available on a USB key, because sometimes it might be too much for universities or schools to download that much data in one go. And that has full documentation, so really step-by-step trying to help students go through how to use the analysis examples and how to benefit from all the different tools. And so many groups within the Atlas collaboration have been using this data, developing their own lab courses at undergraduate level. Okay, so both Atlas and CMS have been using Jupyter technologies. This is a really wonderful tool where you can make root books to execute and run your own analysis directly in your browser. So you don't need the virtual machine, you don't need to have root downloaded. So here's an example from CMS and Atlas. So this is all in a browser, you have all the code in place and they create the plots. Then you can change around the code, you can put in your own plots and that will change the plots directly. So you can run, edit, and save your own root books, and this is incredibly successful, and both experiments are really trying to expand the use of the Jupyter notebooks. Okay, so the next challenge I want to talk about is how do we celebrate better our collaboration and also diversity. So all the experiments work hard on talking about our collaboration, the different people within it. So there's been many articles, blogs, photographs, looking at diversity of the collaboration and of the students. There's also been a lot of celebration of the women in the different collaborations. For International Women's Day, Atlas has done a selection of photographs, and they also did just this year a video for International Women's Day just showing a selection of female physicists within the collaboration, and it was one of the most successful videos we ever did, over 100,000 views over several platforms. Earlier this month, there was the first International Day of LGBTQ, so I'm sure we'll hear a bit more of this in the diversity talk, but all the different collaborations changed their logos and gave short posts about the support for the day, and at CERN, if anyone was there, you would have seen there was a very nice cake stand also celebrating diversity at CERN. Okay, so we also want to look at how to engage new audiences. So a lot through our outreach, we'll often be always looking at people who are already engaged and interested in physics and in what we're doing at LHC. So how do we engage new audiences? How do we interact with people who maybe aren't so readily interested in science and what we're doing at the LHC? So there's many ways of doing this. I mentioned some before, but what I'm going to highlight here is going to run events at music festivals. So this is something that CERN are running in collaboration with Atlas and CMS. So this particular one is WOMAD in the UK. So this is a festival of music and dance. But now they have this physics tent. This is a physics pavilion. They have these two giant tents, which are absolutely fully packed every single day of the festival. So they have 6 talks each of the 3 days, all about different areas of physics. And as I say, they're always completely packed. They have another tent where they do experiments, they have demonstrations, they have a lot of things from CMS and Atlas where they can do virtual reality and interact with the experiments. So over 5,000 people came to this, and it's a nice way of interacting with people that maybe aren't so readily interested in science. Okay, another way to interact with new audiences is, of course, online, and one of the key ways that they're doing, the experiments are doing this, is using Instagram. So of course they're using all the other platforms, but I'm going to just focus on Instagram for this particular example. So Instagram is specifically something that a lot of younger audiences are interested in, and it's very nice. You have photographs and short videos that you can use. So this is the Alice page. You can see everything looks it's very nice, it's very pleasing to the eye, and you have very short posts. The idea is really to engage young people. It's not to teach them suddenly about particle physics in one go, just to give them some nice pictures. You can see on the Alice, they have a nice picture here of quark matter, and it should engage people, maybe plant ideas in their mind to maybe follow up further. They do certain things like the Throwback Thursdays that LHCb and CMS do. So this is really nice. Each Thursday they share a photograph of the making of CMS right from the very beginning to current day, and they give various anecdotes. So this is a very nice way, again, of engaging people in the experiment. And Atlas and CMS also do these stories. You can see just on the right side, we had a young PhD student showing people around what we're doing here at ICHAP. Okay, and then of course there's Art Meets Science. So some of you probably have heard of the Art at CERN organization. So they do a lot of the collision between art and science, and again it's a fantastic way of really tapping into a way that different types of people can interact with the physics that we do at the LHC. One of the most recent very nice collaborations was called the Halo collaboration. So this was from some artists at residence called Semiconductor who worked at Art at CERN, and from that they began to work with some Atlas physicists and use Atlas data to create this beautiful installation, which is at Art Basel. So you have these, in the top, it's a kaleidoscope of light showing particle interactions and collisions from minimum bias data from the Atlas experiment, and it's connected to these 4-meter-long piano keys, and as they interact with the perimeter, it creates sound. So it's an immersive experience for people to interact with the Atlas experiment in a new and unusual way. So CMS really do lead the field in looking at how to engage young people, especially through art with their experiment. So there was recently an exhibition in Canada, the Cultural Collisions exhibition, and one of the fantastic things CMS ran there, and they've also ran in various other places, is doing workshops with school students where they create science-related art. So they have a set of lectures about particle physics, about Atlas. They get to interact with some of the materials that CMS make, and then they get to make their own exhibition. So it's a great way of young people being able to be creative while thinking about and interacting with particle physics. So that's all I have. Just to summarize, I think there's a wealth of work being done. I didn't get time to touch on a lot of the different things going on in different experiments. So there's a lot of work being done to engage society with our wonderful world of LHC physics. But we really must support outreach and education more, and I think especially our institutes and our policymakers in our various countries must be pushed to encourage this. We need to work on the various challenges that I highlighted, especially maybe engaging in new audiences and improving diversity in our field. And I think there needs to be more recognition, especially for young people who are engaged in outreach. Okay, so thank you very much.
So it's very great what you showed here, but it seems to be a lot of work behind it. Is it all done by the researchers in their free time, or do you have special persons engaged in this? And if yes, how many resources are put in there? And what is the implication for smaller experiments, maybe, which are not based in CERN?
So the 4 experiments work slightly differently, but we try to give the impression that outreach and education shouldn't be something that people do in their own time. It should be intrinsic to every experiment, just as every other component of an experiment is needed for it to work. So education outreach, we encourage in all the experiments that physicists spend just a small portion of their time doing something to support these roles. Of course, many of them do have experts that are not physicists to support them in core work, but a lot of it is done by physicists. And we hope that this also does propagate to maybe some of the smaller or other experiments around the world. It shouldn't be something that's given out of the experiment. We're the physicists, and we should be there to communicate and to create resources that we need for our experiment.
Excellent presentation. I really appreciated that. I look at the wealth of information you presented, and the one thing I sort of ask myself is, how do I know that everything is working? And behind everything, because it seems to be done by experiment, how do we know that there's enough cross-communication to decide that, well, we tried that for a year, let's marshal our resources to something that's a little bit more effective so we can continue to innovate?
Yeah, that's a very good point. So between the experiments, we interact, I'd say, quite a lot. We all have different ideas, so some of the 4 experiments might be pushing one area, and the other ones might see how it goes and follow suit. And I think that works really well, that some of them are stronger in different areas, and we all support each other, and we all share our, of course we do, it's education outreach, there's no need for competition when it's about communicating our science.
Any other questions? Yeah, yes.
So you've shown a lot of great resources that are available to bring people in. What about those of us who wish to be engaged more, either from within an experiment or want to build a new level of outreach in our institutions? What resources are available for us to be able to make that step?
Yeah, so each of the experiments has an outreach group that's exactly there to support you in the work you do in your institute, and we'll welcome you in, of course, to help with the core work, of course. So yeah, if you're interested, you need to speak to your outreach contacts in your experiment, and yeah, they're there to really support you and help you as much as you need.
Thank you.
If not, let's thank Kate again. The last talk of the session is on diversity by Sahal Yaqub from Cape Town.
I am not an expert on diversity and inclusion. I'm a high-energy physicist who's passionate about this work and thinks that it's important. So before I go into the summaries of the session, I hope you will permit me to explain to you, or to share with you, why I think diversity and inclusion is vitally important to all of us in this room. This is our wonderful world of high-energy physics. We consider and test remarkable models of the universe that exhibit a rich phenomenology. We've seen multi-messenger astrophysics, standard model precision measurements down to incredible accuracy, and searches for things like leptoquarks, supersymmetry, and quantum gravity. We've also seen incredible technological planning and foresight. This is another view of the world we live in. The items marked in yellow in various regions are the leading killers of people in those regions. The bars in yellow are communicable, maternal, prenatal, and nutritional conditions. In a nutshell, that means these are conditions that can be eradicated with adequate access to resources. And you can see that by just looking at the fact that they're the leading killers in the African region with low income, less of an issue in Southeast Asia, and even less of an issue in Western Europe. According to the World Bank and the World Health Organization, half the world lacks access to these essential services, and 100 million people are pushed into extreme poverty because of health expenses. Fundamental to achieving universal health coverage is equity, and there's some text talking about the importance of health coverage for women and girls the world over. To be able to do what we do, to be able to do particle physics in this world, is a huge privilege and a luxury. We're lucky that it is a luxury that also provides a benefit to the world. Application of the scientific method, greater understanding of the fundamental physical laws, and technological advancements in high-energy physics have had substantial impact on society, like particle therapy for cancer and the development of the internet and electronics. We make the argument reasonably often, you've heard it during this week, that what we do is built into human nature, a search for a global truth that has value not just because of the truth we seek, but because the search itself is a fundamental pillar of our experience as a species, the human experience. If we truly believe this, it is unconscionable that in this environment, this grand pursuit, this luxury, is available to only a few. As we become a larger and more resourceful community, able to exist beyond physical boundaries through telecommunication, we have a responsibility to ensure that we truly encompass all of humanity for the leadership, generation, and dissemination of our work. The only other options are that humanity only encompasses the current cultural and demographic majorities in high-energy physics, that the rest of the world then is subhuman, or that the privileged have a right to protect their privilege because they earned it by some historical virtue. To be a diverse community is to be composed of different elements, and diversity is characterized by the relative number of each diverse element in a community. One achieves diversity by behaving in an inclusive way. That is to say, actively behaving in a way that encourages people with characteristics which are unusual in our community to join our community. The parameter space for diversity is slightly smaller than that of supersymmetry. The obvious aspects to consider in diversity are sex, region, race, culture, sexual orientation, and income. To be inclusive means more than just to address these particular aspects of diversity. Expectations of our colleagues must be reasonable in terms of deadlines, workplace satisfaction, and overall stress. Students and postdocs should not come to the end of their time with us feeling close to depression or burnout. The argument that previous generations had to deal with similar stresses and therefore we do not need to improve our environment is fatally flawed. with that, let's go to some of the highlights from the parallel session on diversity. Maria Grazia Pia started with a scientometric analysis of our publications, and she showed that over time, there are more organizations publishing, there are more authors publishing, and there are more countries publishing in particle and field physics. She then took this a bit deeper and looked at who is publishing. So on our y-axis here is, that is not the button I wanted to press. On our y-axis is the number of publications, our x-axis is time, and we're looking at the number of publications for countries, organizations, journals, and authors. The box plot shows us an apparent contradiction that we have a low and approximately constant median, even though the mean is rising, and we have many outliers outside of the 3 sigma. Maria Grazia pointed out that this has particularly sociological implications for the expectations of new individual researchers coming into the field who might be expected to match the average rather than the median. We can then look at how equal we are. So the GD index is one of the common measures of how equal we are, and it's basically the X richest people in the world are worth more than the poorest Y%. If you're at 0, you're perfectly equal. If you're at 1, you're perfectly unequal. On this plot, we see the perfect equality line, and then the Lorentz line is the curve that will describe the distribution we're talking about. The Gini index is essentially the ratio of the area between a perfect equality and the Lorentz curve and the total area in the bottom half of the plot. If we consider the number of publications as our wealth, we see that per country, our inequality has been decreasing through the years. As we move from 2000 to 2017, inequality has decreased. If we look per organization, so something like INFN or CERN, we see that throughout time, our inequality has increased. So there are fewer organizations who have more of the publication wealth. We can do the same thing looking at the numbers of journals, and there the numbers are inconclusive, or at authors, and we see a similar thing as we see for organizations, that the inequality is increasing over time. So a smaller fraction of authors are having more of the publications. Brian Beckford talked to us about underrepresented minorities in the United States. He started by talking about the percentage of women in physics, and he showed this wonderful plot that shows the increase in the percentage of women from 1965 through 2015. Nobody asked him about this dip in bachelors here, but PhDs luckily at least continue to rise. But Brian went further. He broke this down by race. And when you look by race, you see that most of this increase was driven by white American females, and that other underrepresented minorities stayed essentially flat over a similar period. Keeping in mind that African Americans comprise approximately 13% of the US population, we can look at the number of PhDs granted by racial demographic, divided into women and men, and we see that the number of black PhDs granted is about 2 orders of magnitude smaller than the number of white PhDs granted. They don't see a similar thing with Hispanic communities, and so Brian went into details of a plan to particularly bring more African Americans into physics. Right? So the essential information he showed us was that while there has been an increase in Bachelor of Science degrees for African Americans, less of that increase has come through into physics, so there's been an overall decline in physics PhD degrees amongst the African American communities. So there's something called Team Up. It's a nice acronym, and it's in Brian's slide if you really care what it means. It was formed in fall of 2017. I'm sorry about the typo. to examine and assess regions for the persistent underrepresentation of African Americans in physics and astronomy at the undergraduate level. And they have a long-term goal to increase the overall participation rate from 4% to 9% or into that range. And they're going to produce a report that will include findings from their study, institutional case studies, and innovative programs and student narratives. So this is going to be achieved without ignoring prior research, including surveys and site visits, and all of you in this room can help by distributing the survey to your African American students, sharing any information you have with the task force on innovative programs that have increased African American undergraduate participation, and sharing your ideas for solving the problem. We had a talk from Genevieve Guinaud from CERN. She told us about the CERN Teachers Programs, where groups of international teachers come to CERN and get taught to better teach physics. Okay. She highlighted at the start that coming out of high school, we see a small percentage of women in the UK choosing to pursue physics. And they identified this as a problem. So the CERN Teacher Program encourages school kids, and in particular girls, in response to the information they had from the UK, and I'm sure it's true in other countries, to take up science subjects, to contribute to the reduction of the gender gap in the field by raising awareness on gender equality in STEM and physics, helping teachers rethink their teaching methods, learning from each other, and then sharing the tools they've developed for an inclusive classroom. They assume the teachers haven't already been trained to teach to a diverse audience, and they use the amplification power of the teachers' community, so getting the teachers together to talk to each other. Some examples of what they do: they share experiences in the classroom, they introduce new concepts, and they test their application in mock classrooms. They have input from research and practices, so the teachers get to meet with experts and explore research papers, and they get to interview female scientists at CERN, and they share information on initiatives and look at data. In order to establish change and make sure it happens, whatever they work on in the classroom needs to be disseminated out into the community. So here are some examples of actions implemented by previous participants. So there have been open activities like attendance at science fairs to teach the scientific method, a buddy system for higher grades, the introduction of reflection time and open inquiry activities, and the implementation of an alternative way to prepare students for evaluation. In order to disseminate the lessons learned from the 2016 work group, there's a leaflet which helpfully lists country-specific approaches, learnings from the interviews, and advice on how to support a gender-inclusive environment in the physics classroom. And the 2017 work group has a website where you can see their latest output. The teachers have particularly commented that the introduction of reflection time has been key, introducing collaborative ideas rather than competitive ideas amongst the classroom, encouraging people to work in groups, avoiding stereotypes and biases in their teaching, letting the students do inquiry activities and encouraging debate rather than rote learning, avoiding painting science pink, and encouraging role models. Simon Akar from LHCb told us about the early career gender and diversity I forget what they are called. There's a word. It's on there on the slide somewhere, excuse me. Offices. The Office of Early Career Gender Diversity. So they advise the LHCb management on early career gender and diversity issues. They're also available to listen to and advise colleagues in a confidential manner who feel they've been victims of unwarranted behavior. They collect statistics on what's happening in the collaboration and then publicize those statistics. They're careful not to alienate people. They want to be inclusive and not attack people. And they regularly organize meetings with the collaboration and support newcomers to LHCb. In general, they're a data collection and consulting group. Practically, they understand that they reflect the international community and they cannot change the culture on their own. They can reduce obstacles and sources of inequality within the collaboration. And Simon particularly mentioned explicit discriminations, which are easy to spot, and implicit discrimination, which is less obvious to spot, but also vitally important. He also focused that we need to not just identify problems, but fix them. And he raised the issue about parental leave, for example, as something that came through from the ECGD, where conveners now had access to parental leave, and when they came back, they could return and resume their mandate. If people were offered a talk, they could decline the talk, and there was no ill effect to that decision. The Atlas collaboration showed some of their regional and gender demographics. So here we see the number of Atlas that is not showing up very well, members on the left and authors on the right from various regions. The center is the United States, then there's Northern Europe, the Mediterranean. We move down to Eastern Europe, Asia, and Africa, and you can see the total number of people. And in the bottom plot, we have the ratio of male to female members. The dashed line is the average membership on Atlas. The solid line is the average membership from people over 35 years old. And we see that there's some large variations across the regions about this line. Obviously, the average has to come out the same. Atlas also showed their age demographics. So they appear to be getting younger, which makes sense, but also in the younger cohort, they have a higher fraction of women, and we hope that as time goes on, these continue to migrate across, and we keep more women in the field. Atlas presented the diversity of leadership positions. In general, going down the x-axis is less important. So these are the more highly responsible areas, moving now to lower responsibility areas. And then we can look at the fraction of women represented in these leadership roles. And again, we have the Atlas average fraction of women. And we can see that the fraction in these leadership roles is similar to the average fraction of women in those roles. LHCb and Atlas also spoke about who are LHC and Atlas in terms of their regional diversity. The blue color on both maps are countries that have institutes which are part of LHCb and Atlas. The green on the Atlas side are countries that don't have institutes that are members, but have at least one individual who is a national of that country who works in Atlas. It's clear to see there's a big hole right there. And following on from that, we had a talk from Azwandini Maranga about physics diversity and inclusion in Africa. Africa has a range of diverse challenges, basically poverty, inequality, and unemployment. Azwandini told us about his belief in the power of having an educated community and population in addressing these issues. And he highlighted the fact also that during apartheid South Africa, the majority African population was legally prohibited from studying the mathematical sciences. In Southern Africa and the Global South generally, there's a big new project. It's the SKA, the Square Kilometre Array, the largest radio astronomy observatory co-hosted by South Africa and Australia. We hope that this is going to have a huge effect on the nature and culture of global collaboration being housed in the South, and this is leveraged off South Africa's geographical advantage for astrophysics, pointing south and having a big tract of land in the middle that has been undeveloped. Other direct interventions include the African Conference of Fundamental Physics and Applications, which is happening for the first time this year, and we connected to it from ICHEP, but also the Associated School that's happened a bit more often, which brings in students from around Africa and researchers from around the world, and has seen a big uptake, at least for me in Cape Town, of students making contact and say, yes, they'd like to continue and study physics. The South African Institute of Physics has a Women in Physics lunch conversation every year at their annual conference, and feedback has been that this has been a good place for women to talk to each other about the issues they face, how to overcome that, and be more comfortable continuing in physics. Genevieve also told us about fixing the work culture at CERN, implementing policies to help the organization move away from normative views on families and career commitments. So she highlighted that this old idea of an ideal family, including a married man and a housewife with children living under the same roof, is completely fractured. So there are many benefits that you could get by being part of the CERN family that were only available to you completely if you were married. They changed this so that registered partners are recognized irrespective of the country of recognition. They have equal treatment now for the installation irrespective of the spouse or partner moving with the person, so they're better able to support dual career families and measures to ease social integration. They've made paternity leave gender neutral, but under questioning, Genevieve mentioned that it's not the same amount of leave, it's just that both genders can take leave. In terms of work-life balance, the idea of sacrificing life to work has gone away a little bit. So CERN is allowing increased flexibility for new parents, increased flexibility to the leave scheme, and increased flexibility into a teleworking program. I think this was very important. The policies don't matter. If the people implementing the policies don't describe to the values that underline the policies, the culture in the institution and the way people feel isn't going to change. It's not the rules that affect people, it's the application of the rules in the society around them. Of course, if the rules are bad, then we have other problems. Okay. I am missing a slide. That is unfortunate. So, Daniel talked to us from the Port. The Port is an NGO based at CERN that aims to translate physicists and physics work outside of the lab into areas where they need to be. Sorry, Chair, you're showing me 3 minutes and I've just been told to stop. So I'm not sure who to listen to.
3 minutes.
Thank you. Okay, great. So, the Port is an NGO based at CERN. Daniel Dobos came in and spoke to us about the difference in what they do. Daniel related what the Port does to how outreach is done by CERN, and based on Kate's talk, Daniel didn't get it entirely right, or I misunderstood, but Daniel spoke about CERN visits. Daniel mentioned CERN visits as a key factor of bringing industry into CERN, bringing people into CERN, explaining to them what we do, why we do it, and how it affects them. And he explained that on the Port, they go out. They take the scientists, they take themselves out of their comfort zones, they meet society and communities in the regions where the problems are, and try to, using our skills, try to sculpt solutions to their problems. So we'll go through some of their solutions. They built a better body bag. This is a key solution in places where people die, are killed, unfortunately, far away from mortuaries or cold storage, because decomposition of the body makes it hard to identify the body, which is a problem medically for finding out why people died, and also personally for knowing if people have died, unfortunately. And so they've built a better body bag. They've built smart dogs. They haven't actually implanted chips into the dogs. They've developed these packs that go on the back of explosive sniffing dogs. So there are many previously war-torn areas that have landmines in innocuous areas that can hurt people. And sniffer dogs are used to find these. They're normally on a leash, and they're limited by the speed of the human with them. The smart dog harness allows the dog to travel faster, cover a larger range, while the operator, the handler of the dog, has a remote unit to issue commands and see what the dog is seeing. And the last thing he mentioned to us was an intervention to help children with UV hypersensitivity. So apparently there are children who, spending a minute in the sun, would contract skin cancer, and the Port helped come up with a solution to allow them to go outside. So what can we do? This is a slightly modified slide from Brian Beckford. We need a broad community-wide effort generally. Individuals from marginalized groups have always been tasked with fixing the problems while suffering through them. You can stop all harassment, learn and be involved, advocate, mentor, recruit more diverse people, and implement policies that support inclusion and equity. We are no strangers to challenges that are daunting, span decades, to challenges that are daunting and span decades and are incredibly valuable and fulfilling once complete. The challenges of diversity and inclusion are ones we must rise to meet. Thank you.
At the map of the atlas, is there the member of North Korea?
I don't know. So this was from 2016.
There is the color of the green.
Oh,
in
green.
North Korea.
So in North Korea. Okay. Luckily, I can say, let me go back. Take this up with Louise. No, I'm a member of Atlas. I'm sorry if we made that mistake. I'll make sure if we regenerate this plot, we fix it.
Any other questions? Well, let's thank the speaker again.
Good evening. Let's resume the session. We invited a very special person this evening. He's from one of us, since he did his undergraduate major in physics. Then he went to graduate school for EE. So let's welcome the Senior Vice President of Samsung Electronics, Dr. Eun-Soo Shim.
Hello. Thank you for kind introduction. As introduced, my name is Eun-Soo Shim, and I did really graduate from physics department for bachelor, and also I earned Master of Science degree. Then I found physics was too hard, so I changed to easier field. So now I've been working on mostly computer technologies. More than about 20 years. Now I'm working for Samsung Electronics, which is known for its semiconductor product and also smartphones, TVs, and so on. Today, I'd like to give a brief introduction to the R&D center I belong to, which is Samsung Advanced Institute of Technology. That is a corporate research arm for the company. Then let me introduce the R&D activities on AI in the institute. Mostly that is happening in my lab. The Samsung is a very complicated organization actually. Internally, sometimes we feel there are multiple Samsungs. It's not just one Samsung. Anyway, we have many campuses in Korea, and my institute is located in city of Suwon, which is about 30 kilometers south from Seoul. We were established in 1987 as a corporate R&D center, initially serving the whole Samsung conglomerate. Now we more focus on Samsung Electronics and also other electronics-related Samsung family companies. And these slides show some of the noticeable achievement of the institute since its establishment. MLCC is widely used in modern electronics devices. And recently, we started to focus on AI technologies, and we actually developed successfully few AI technologies that are now being deployed in our product. So actually, if you use Galaxy smartphones, then you can experience some of the technologies we developed, including speech recognition and fingerprint authentication, and also face authentication. As I just mentioned, AI is now big thing in the institute, and we are working very hard at and also transferring our technologies to the product. And so also we develop OLED technologies that is also being used for our OLED displays of the smartphones, and we are working on graphene very actively. It looks like our graphene group is one of the most active research groups on graphene. And also Samsung TV has a brand name QLED. The Q stands for actually quantum dot, and that quantum dot technology was created in our institute. So now it's core technology for our TV displays and also TV product in overall. And if we select few of the key themes in the domain of device and material, we can say smart driving and innovative mobile device, immersive display, and next generation semiconductor are the key themes. And for smart driving, we are working on autonomous driving algorithms and also neural processor to power autonomous driving system. And also we are working on new generation of infotainment system, including augmented reality 3D HUD head-up display system. Also, we are working on battery technologies very actively. Automotive battery is going to be a huge market, so a lot of companies are investing in it, and Samsung is one of the also key players in the battery industry. Samsung is unique in the sense that we have business of semiconductors to TVs and smartphones. So we have really vertical integration of a lot of technology components to build consumer products. And a sensor is being widely used and is becoming more and more important, especially AI is also making sensor essential component for a lot of electronic devices, and we are working on many new type of sensor technologies. And display material is also a key technology for our display products. And we are working on graphene and also high-K materials. This is going to be an important technology to overcome the challenge of making semiconductor smaller. Now, a lot of people are expecting that Moore's law almost stopped, and we are not going to be able to reduce the dimension of semiconductors any further in the very near future. And we are trying to overcome that barrier. And neural-network computing and quantum computing are also important topic for our future. So we are investing in that area, and robot and environment solutions. We have a lot of factories, and the factories generate a lot of pollution materials, and we do our best to reduce the impact on the environment, and we are now working to biology-based solutions to remove pollution materials. We have supercomputer and also nanoscale analysis equipment, and also we have our own labs in our campus. And so we also have active collaboration with academia, and we established AI lab at University of Montreal. Professor Yusup Benjo is one of the most prominent researchers in the field of deep learning. Jeff Hinton is another, and Yannick Kuhn is probably the last. So among three, we are collaborating with Yannick and Yusup Benjo, and he is Professor Yusup Benjo. So it's not just AI field. We have active collaboration on a number of topics which we consider strategic for our future. That include stretchable electronics and 2D device. You might be familiar to these physics professors. And we have number of branches on many locations. So this is brief introduction to our institute, and let me introduce our activities on AI technologies. Anyone heard of Bixby? Can you raise your hand? Okay, yeah, few. No, thank you for knowing our brand for our key AI products. The Bixby is the name of virtual assistant available on Samsung product, including smartphones, TVs, and washing machines and air conditioners. Bixby is similar to Alexa or Siri and so on. You name big IT companies, and they must be working on their virtual assistants or either adopt virtual assistant from somebody else. And we have our own virtual assistant. The name is Bixby, and the Bixby provides the 4 key features. Obviously, voice is the main interface for the virtual assistant, and that requires speech recognition and natural language understanding, dialogue management, and action planning. All these technologies are developed in-house. And these technologies are being used by Bixby service at the moment, and also we are continuously improving these technologies. Among these, the speech recognition and natural language understanding technologies were developed at SAID, the institute I belong to, and were transferred to the business unit and being used in our product. And also, we are working on machine translation as well. This chart shows the accuracy of our speech recognition engine in comparison to a competitor. At the time of July 1916, we have updated data, but this shows the direction we are pushing. One of the key challenges for speech recognition is maintaining accuracy at a noisy environment. Nowadays, speech recognition is quite developed, and a lot of people find it now usable. The problem is that in an environment like this, where this is very quiet, speech recognition works well in most cases. But when you use virtual assistants with speech in a noisy environment, you can notice the accuracy drops significantly. So we try to maintain the accuracy in a noisy environment. So this speech noise ratio at 5 decibel, with this blue bar is the performance of our technology, and the red bar is that of our key competitor. And you can see these are our competitors, and the blue bar is the performance at a quiet environment, and red bar is the performance at a noisy environment. And you see we relatively maintain the accuracy in a noisy environment compared to our competitors. So this is our performance at the noisy environment, and this is performance of computer A at a noisy environment. And we adopted LSTM as our base for the speech recognition acoustic model in 2013. The deep learning became quite noticeable in the year of 2012 when Stanford and Google team published paper about detecting cats using a cluster of machines. We started to develop our own speech recognition engine using deep learning in 2013 and 2012 at the time, most of the companies were using DBN or DNN for the speech recognition engine, and we thought speech was a sequential pattern, so why do we use DNN? We should use RNN. Then we thought LSM would be a nice choice, and we tried LSM and found that it really worked very well. Now, actually, we are using different technology for our speech recognition. And also, natural language understanding is still a big issue. This has been research topic in the AI field for a long time, and we made big progress in speech recognition, but still the progress in natural language is relatively very small. You can use Bixby, Google Assistant, and so on. Still, a lot of dialogues are based on scripts and keyword-based scenarios. So if you tweak some of the keyword, then the virtual assistant really doesn't understand what you are saying. And also dialogue becomes out of context very often. So we are trying to overcome that issue, and one of the key issues is also understanding context and also incorporating knowledge base. I think that is probably one of the key differences between the AI technology and human intelligence. We have a huge pile of accumulated knowledge base, and we observe it and we use it when we understand the environment. But the current AI technology cannot do it. We don't know how to do it in a scalable fashion. So now current AI is mostly very narrowly defined task solver. And also it's a pattern recognition engine, fundamentally. So you have to create a training set that contains good description of the patterns you want to make the machine recognize or solve. And it cannot really utilize the knowledge base human beings established and accumulated. So LSM used to be the core technology to solve sequential pattern problems. Now, this is called self-attention. It's basically fully connected layers with attentions in between each layers. And this is actually much more effective in solving sequential pattern recognition problems. Let me show a video showing the comparison of machine translation engines developed by us and also to other companies. Well, it's in Korean, I'm sorry. This is translating Korean to Chinese and Chinese to Korean.
근처에 광동놀이 잘하는 곳 추천해 주세요. 뜨끈한 국물 요리가 먹고 싶은데 어떤 게 좋을까요?
Why do this? Let's say I don't speak Chinese. I want to use machine translation when I travel in China, and I turn on machine translation from Korean to Chinese, and I don't know whether the translation is correct or not. Right? So this is a simple way to check whether the translation is working properly. So it's the reverse translation. non-Korean speaking audiences can do just pattern matching. Pattern matching. Right, here, this is saying, I want hot soup. What would be a nice choice? This is the question in Korean. And it was translated to Chinese, and it was translated back to Korean. And this shows almost same sentence with the original sentence. Now we are making comparison with Google and Naver. Naver is a portal in Korea. Now we are claiming that our translation engine is better than Google's and Naver's. Probably this is not really fair comparison. No, there is no public benchmark, right? So this is just our test case. Anyway. And we are using this engine internally. We do a lot of translation between different languages. We have branches all over the world. And biometrics. Biometrics used to be technologies for non-consumer electronics industries, mostly military and government and so on. But as mobile payment is adopted, biometrics became an essential technology for consumer electronics, especially mobile devices. And we developed face recognition, iris authentication, fingerprint authentication. All these are already available on our smartphones. For example, this is the latest Galaxy phone, S9, and the screen is locked. I just turn and right. So instead of asking me to type password or pattern, if that device sees my face, it unlocks the screen by itself. So all these technologies are developed in-house, and face recognition and fingerprint authentications were developed in my institute. And we are working on speaker verification. Many people think that is the ultimate biometrics. So you don't have to touch anything, you don't have to look at anything, just you say few words, then the device recognizes you and it allows you to access the device. It turns out speech verification, the speaker verification is probably one of the most difficult problems in biometrics. And some people think probably it's impossible to do speaker verification reliably. Maybe our voice doesn't have enough information that can allow us to distinguish one person from the other. Well, still, this is very attractive way of doing authentication, so we are still investigating this. Now, face recognition is now very widely used in China. Actually, if you enter China and in the immigration desk, actually they capture your face. The US does the same thing, Korea does the same thing. And actually, at the time, you are contributing your face image to the database of China. They use your image as a training data for their face recognition algorithm. Do you think these two pictures are the picture of same people, but same person, different people? I mean, all these pairs. So, same person. Yeah. Different people. Actually, they are the same person. So many of them, many of you are right. Actually, surprisingly, these two photos are of the same person. So the posture illumination and occlusion make face recognition difficult. And how about these pairs? Do you think these are of the same person or different people? Can you try again? Same person. Different people. Yeah, they are the same person. How about these pairs? Okay, this is the last. Doing this. You could enjoy again. Same person. Yeah. Different people. Yeah, they are different people. Actually, twins are almost impossible to distinguish from images. So that's one of the remaining challenges for face authentication. Other than that, I think now this face authentication is up to the level of fingerprint authentication, we believe, or at least near that level of reliability. Right. Also means this is, person is recognized as the registered user. And reject means this is different from the registered user. We try to support face authentication even in a dark room. That is quite challenging. We are still improving the performance. Now, one of the issues with biometrics is that quite often the people can fake the information. It takes effort. So most people won't do it, but if there is a financial interest or any other strong interest, then people can try it. One VGA is using a printed photo. So it detected that it's not real person. So different type of print material. And also you can use video. And 3D shape. Now people actually can make 3D shape with silicone that has quite similar texture as human skin. We are trying to detect that case as well. So this is ongoing battle. Also, people face changes slightly over the time. So we actually adapt our model as we see more data of the user. So that has been implemented and being used. And autonomous driving. So this shows the definition of autonomous driving levels. So the level 5 is so-called fully autonomous driving, where a lot of people think when they hear about autonomous driving. So in that stage, actually, we don't need to have a wheel. The people can just sleep, and the car will take from door to door in any condition. So that's the ultimate level of autonomous driving. And we have level 4, level 3. So this is easy way to distinguish the levels, different levels. So now in level 1, still you have to hold your wheel and you have to pay attention forward. And in level 2, you can do something else with your hands for a short period of time, and also your eyes can look around short period of time. So actually, you can see your instant messengers even check emails if it can be done relatively easily. In level 3, now you don't have to really all fear. And maybe you can read books. And level 4, now you can go to sleep, but in a limited environment. Do you think we'll ever reach this level? This fully autonomous driving, so that you don't have to learn driving at all? Okay, no, I break my promise. I believe we can reach this level. Wow, okay. Yeah. Oh, no, no way, no. We have to still learn driving. This is very interesting. Usually, professors are cautious. They are conservative. Actually, many academians working on this field think it will be almost impossible to reach this level. And people like me who are not very careful think, oh, why not? We will to reach this level. After few accidents in recent months, Tesla had an accident, Uber had an accident. Now the optimism went down, significantly here and there. So now, just at the end of last year, many car manufacturers claimed that they would launch level 4 autonomous driving vehicles in 2021 and fully autonomous driving vehicles in 2025. Now, nobody is saying it. They slightly changed their milestones. So now they are talking about level 3 in 2021 and maybe level 4 in 2025. These are the key component technologies to realize autonomous driving. As you see, we need hardware sensors and the algorithms to interpret the data from the sensors and localize the location and all kinds of information to understand the situation and environment. And we need to identify the path and also control the car itself. The software stack to realize autonomous driving is quite complex. These are the hardwares. We need sensors, and also we need robust operating system, and also middleware to facilitate communication between all these different modules. And also we need algorithm for perception and planning, and actual integration of algorithms to realize the functions for autonomous driving or ADAS. And also, we need a map and localization algorithm, and also vehicle-to-vehicle communication or vehicle-to-infrastructure communication. And also, we need a system in the cloud to manage maps and collect data from the vehicles and so on. These are the hard conditions for autonomous vehicles to handle. Actually, these are even hard for human drivers as well. Nobody is claiming that they solve these challenges yet for autonomous driving. So most demonstration of autonomous driving is on highways in a sunny day. And to be able to reach level 5, we should solve all these conditions. And map is very important for autonomous driving because you need to identify paths and also need to know the location of the vehicle. And humans use this kind of map for driving. And most of the autonomous vehicles being tested on the road use this kind of high definition map. The maps Google use are looking like this, and they actually correct the location of, let's say, traffic signs and traffic lights manually, and it has precision of centimeters. And we started to work on autonomous driving about 3 years ago. And we know most of the companies are using this high definition map as the base for their autonomous vehicle or autonomous driving system. But we thought differently. It would be very expensive to construct such a high definition map to cover the whole country or the whole continent. And it will be even more difficult to maintain the accuracy of the map. And humans use just 2D navigation map to drive, so the machine should be able to do the same. So we decide to develop our autonomous driving technology that use just 2D navigation map for actual driving. That is our strategy. And segmentation is actually identifying the class of each pixel in the image. This saying, our segmentation algorithm is performing very well in some benchmarks, Kitty Road benchmark and Cityscape benchmark. I think it was the result of our algorithm tests this month or last month. This is a road scene taken in a German city. This is widely used public benchmark data set, and this shows the result of segmentation. The red ones are pedestrians, and the blue ones vehicles, and road, and sidewalks. Obviously, you should be able to detect all the important objects, including vehicles and pedestrians. Eventually, you should be able to detect small animals like cats, and also you should be able to distinguish flying paper from rock. We are working on object detection for various weather conditions. This is a road scene in the city of Suwon, where our campus is located. And this is the object detection result on a rainy day condition. So these are traffic lights and traffic signs. There will be pedestrian somewhere. Right, this is a pedestrian. And rain is most important information for autonomous driving. So you should to identify lanes in all conditions. And also you should identify where the surrounding vehicles driving, right? So be sure to map the vehicle in your camera to the lanes on the road. So this is showing that we are using just mono camera to detect vehicles and lanes and map the vehicle into the lane and also measure the distance. Typically, people use powerful machines to develop deep learning-based algorithms, but when we apply the developed models, eventually we have to work with the hardware resource available in the application scenario. And this is the case for vehicles. So we have to run all these complex neural net models on an embedded computer inside the vehicle. So we need to lighten the neural network model. So we work very hard to make our model lighter and still maintain accuracy. So this is comparison with some of the latest models that claim is a small model size with high accuracy, and we beat these models. Simulation is an important technology for developing autonomous driving system, because you cannot have enough road test mileage to guarantee the technology is as capable as human drivers. So you have to use a lot of simulations. Also, rare situations like accident. You cannot really try that on a real road with a real vehicle. So simulation is an important tool, and we have our own small-scale simulation system. And we are looking for large-scale simulation system to facilitate our technology development. And these are the test vehicles we have. This is highway in Korea. That's Gyeongbuk Road. Gyeongbuk. And it's changing. The direction to another highway. So it's taking ramps. When I took the first trip on our test vehicle on the highway, it was a lot of fun. It's full of thrills. This is also an important tool to develop AI technologies. Most of the people are using now deep learning to develop their AI algorithms, and to be able to train neural network with a large amount of data set, you should be able to use multiple servers and GPUs to train the network quickly. And if you just use open source development framework like Caffe or TensorFlow, it doesn't support multi-node disparate training very well. You can try it, but the efficiency is terrible. So if you use 100 GPUs, then you may get just benefit of 40 times or 50 times speed improvement. To be able to use the limited hardware resources efficiently, we should be able to use all the computing power available in our GPU cluster. And this is the result of SCAFE, that is internal modification of open source Caffe to support distributed deep learning training in an efficient fashion. So as you see, now if you use, but the red line is the ideal speed increase for the given use of GPUs, and the actual speed increase is very close to the ideal numbers. And one of the issues with using large number of GPU requires that you need to use large batch size, and if you use just open source Carpet, if you increase the batch size, the accuracy drops. You need to solve this problem to be able to use large numbers of GPUs. And it shows that our version of Carpet maintains accuracy as you increase batch size. As I said earlier, Samsung has business of semiconductors. We are number one DRAM manufacturers and also number one SSD flash memory manufacturer. And also we do have non-memory semiconductor business. CMOS image sensor is a prominent one, and also we have our own so-called application processor. That is a processor powering your smartphones. And we are developing neural processor or neural processing unit to support neural network computations efficiently on our embedded device environment. And you cannot carry these servers on a vehicle, so we need very power efficient processor to support deep learning. And these are the requirements for this new type of processor. And there are many aspects you need to look into to make this processor more power efficient than CPU or GPU. And memory traffic is one of the key issues. And also there is another type of neural network, so-called sparking neural network. That is also called the neuromorphic system. We also have some activities on this type of neural network. There is no clear evidence that this is going to beat artificial neural network. That is the base of the current deep learning technology. But since this is more biology like operation, many people are still looking into this. Well, now this is concluding slide. Now, say this between academia and our business unit, and we actively interact with academia. We observe the research result from academia, and also we add our own ideas into this and create commercially viable technologies. That's the mission my study is taking. And hopefully, we create new experiences and empower people. So this concludes my talk. Thank you.
We have some time for a few questions. I guess we have, okay. Any questions? Yeah.
Hello, so it was very nice presentation. I'm just, delighted. So my question is the following. Your car, when it runs on the road, you have to make sure that it is, 100% secure. So are you testing, for instance, radiation hardness of the FPGA that you are using in the advanced technology? Because, there are well-documented cases, and for instance, where there was an airplane running and flying, and then there was a single event upset event in some FPGA in the plane, and the plane then crashed. So I was wondering, in the car, the situation is similar. We have some complicated logical circuit. There will be some cosmic radiation coming, and it can cause malfunction of the.
Right. The reliability or safety is number one goal of developing any technology for vehicles, especially related to safety. And in autonomous driving, that is a number one requirement. And we know that anything can fail, including hardware and software. You don't need a very special event outside the vehicle. Actually, just the technology just can fail by itself over time. So the key idea of improving safety or trying to guarantee safety or reliability is redundancy.
Yes.
So you have
Some type promoted redundancy or
multiple processors, multiple sensors, or different type of sensors. So for one direction, you don't rely on just one type of sensor. You put cameras, radars, and lidars. And also, OEMs take safety very seriously, so they even try to have redundant computers.
Okay. Okay,
so,
thank you very much. Yes.
So thanks a lot, really nice. Intellectual property is one thing that Samsung and Apple became really experts in, of making patent lawyers very happy in the last years. What is your take on, will artificial intelligence make intellectual property easier or more complicated? Do we start to understand how we handle this? Because in fundamental science, we have a completely different understanding of intellectual property. And as I understand, you're sitting at the interface between academia and using this for industry. So what is your understanding of that?
Okay. Well, since I work for Samsung, let me represent Samsung's attitude about IP, intellectual property. We rarely use intellectual property to attack somebody else. We think we are not in the business of blocking someone from doing business. We try to develop technologies better than somebody else's. So we try to convince our customers by spirit of technology rather than legal limitations. That's, I think, general attitude. In the field of AI, especially the machine learning community, especially deep learning community, it's a little bit special. That's what I found. Many people who drove the development of deep learning are kind of idealists. So they avoided actually patenting many basic ideas. Also, archive is now prime venue for publications, and so probably deep learning, a lot of knowledges and ideas in the field of deep learning are public asset. Anybody can use it. And also, it's going to be very difficult to enforce IP light on key ideas. Unless you look at the source code, you will never know. All right, so this artificial intelligence is a field where the core technologies are probably kind of protected from all this legal hassle. But still, companies are putting a lot of things as IPs surrounding the use of AI core AI technologies. So in the actual business world, still you will have to be careful about IP laws.
Thank you.
So at some point, even if you have redundancy, you're still going to have some failure rate. So is there going to be some criterion that says, well, as soon as we get below some level, maybe the level that humans would have if they were driving, or some kind of level is ready for prime time? Is that the way it's going to work then? How is that going to be decided, I guess that's my question.
Well, this is my personal opinion. It's going to be very difficult to guarantee perfect reliability or anything close to it from experimental data. What is going to happen is that the technology will be deployed step by step, gradually, from an easier environment to a more difficult environment. So we accumulate experiences. And also, we talked about redundancy. And another safety measure is to certainly monitor the system. And if you notice something weird, and the system will try to either park the car or slow down and move the vehicle to a safe spot. So that is actually key requirement for level 4 and level 5 autonomous driving system. So when something goes wrong or it seems going wrong, the car should be able to take these safety measures. But hope the system is, I think we cannot guarantee really complete accident-free autonomous driving system for a long time. But people will accept it if it is as safe as human driving or slightly better than human driver. That's my personal view. Because there is also other benefits. Safety is a fundamental benefit, but also convenience is another huge benefit. I use ADAS when I drive on highways, so I don't have to use my foot to press accelerator and brake. That reduces my stress from driving enormously. So I love that feature. So I know it's not perfect, so I pay attention to the environment. I'm ready to take control, but that still helps me a lot. So autonomous driving is not going to be perfect for a while, but it will be used and still be useful. Yeah, that's my view.
Okay, I think we just ran over the time, so let's stop here and let's thank our speaker again.
Thank you for your attention.